Welcome to Module 27 in this series of lectures on statistical quality assurance and statistical process improvement. We've been talking about Shewhart control charting. The last module was the first part of a technical discussion of the control charting for measurements or so-called variables data. We talked about the X-bar chart and the R chart. In this module, the primary discussion is going to be on alternatives to R charting, that is S charting, and an alternative to X-bar charting, that is median charting, and we'll make a few other comments about issues of control charting for measurements. We will continue to use these data from the previous module, data taken in a Deming drama in IE 361 at Iowa State University. And we're going to now consider an alternative to using and charting ranges. And that is the possibility of charting standard deviations. Charting standard deviations is typically more effective than charting ranges, but the price to be paid is more computation. These days that isn't typically a problem, but the R chart is well entrenched just from force of use over going on 100 years now. But an S chart is a better alternative. In order to figure out what are appropriate control limits for standard deviations, one can make use of a fact that is alluded to in probability courses or basic statistical courses for engineers, that when sampling from a normal distribution, if one takes n-1 times the sample variance and puts it over the population variance, one gets a variable that is chi-square distributed. It turns out to follow from this fact that the sample standard deviation, the square root of S squared, has a mean that's proportional to the standard deviation of the process being sampled. That is, average S is a multiple of sigma, and that constant of proportionality depends on the sample size and is something that is typically called little c4. In addition to that, it turns out that the standard deviation of the sample standard deviation, that is how variable are sample standard deviations, is proportional to the population spread or the population standard deviation, and the constant of proportionality is something that can be computed and tabled and is called little c5. If one takes those constants, little c4 and little c5, and puts them together, a plausible upper control limit for a sample standard deviation is c4 times sigma plus 3 c5 times sigma, with the lower control limit being the same thing, where I simply switch the sign on the 3 c5 sigma. If one adds together c4 and 3 c5, one can rewrite that upper control limit for S as a constant called big B6 times sigma, and similarly, if one writes little c4 minus 3 little c5 as big B5, then the lower control limit for a standard deviation is big B5 times sigma. Further, if in a retrospective situation like the one that in the Deming drama data, if one computes with standard deviations instead of ranges, an estimate of the process standard deviation is then going to be an average sample standard deviation over the control chart constant little c4. You might think that simply taking standard deviations and averaging them, taking S bar, would be appropriate. Well, one needs to fudge that a bit by this multiplier little c4. And if you put those into control limits for the sample standard deviation, put that estimate of sigma in place of sigma, and look at that and say, well, if I collected big B6 over little c4 and called it something, or big B5 over little c4 and called it something else, I might have a slightly simpler looking set of retrospective control limits for sample standard deviations that are these. Again, these formulas are collected at the end of Chapter 3 of Vardaman and Job in a table with other formulas for control chart limits. As one final bit of development regarding retrospective S calculations, if one takes this S bar over little c4 and uses that to estimate sigma, making a retrospective chart now not for S but rather for sample averages, a retrospective X bar chart, one might call the ratio of 3 to little c4 over root n by a name and invent another control chart constant. And if one does that, you can write retrospective control limits for X bar based on an average standard deviation rather than an average range as X double bar plus A3 S bar X double bar minus A3 times S bar. If one takes the scenario of the Deming drama, the brown bag or the red bag has a standard deviation of 1.715, and that means that an upper control limit for S is this number big B6 times sigma, and for a sample of size 5, big B6 is 1.964, and therefore an upper control limit for standard deviations is 3.37. If one looks in a table for big B5, one doesn't find anything listed, and that's because this difference between C4 and 3 times C5 turns out to be negative, and it doesn't make any sense to talk about a negative control limit for a standard deviation. You're encouraged to go look at the data on panel 2, compute standard deviations, and verify these values. But taking them for our present purposes as given, it's only at sample 16 that one begins to see S values that violate this upper control limit for S, the standards given upper control limit for S. If you take the 18 S values and average them, you get 1.72, and multiplying 1.72 by this big B4 control chart constant, that for a sample of size 5 is this number 2.089. A retrospective upper control limit for sample standard deviations is 3.59, and again this 16th sample has a standard deviation that violates that upper control limit. And that says that not only is at sample 16 the process not behaving in standard fashion, but it's just not plausible that there's a single set of parameters that describes the entire 18 samples. That is, there is evidence of process instability. Further, if one was going to make retrospective control charts for X bar based on not ranges but sample standard deviations, there's the value of A3 for a sample of size 5. Here are retrospective control charts for X bar based on S bar, and if one applies those control limits to averages in that dimming drama data, again, there are points outside, there are X bars outside of those limits. There's evidence of process instability. That's an alternative to control charting for ranges. As an alternative for control charting for means, one might think about not plotting means but medians. After all, finding a median only requires putting data in order and picking out a middle value. Turns out that's not really as effective typically as plotting X bars, but there are probably some circumstances in which it might make sense because of computational limitations to plot medians. In order to find appropriate control limits for medians, one needs to know some probability facts about it. It turns out that when sampling from a normal distribution, the sample median has a probability distribution that's a non-standard one. Its average value is the process mean, so average median is process mean, but the standard deviation for the sample median is not simply sigma over root n, the number, the standard deviation for X bar, but it's inflated by a factor kappa. And there's a table of values for kappa given in the Vardaman and Job text that basically make that sigma over n a bit bigger because medians are more variable than are means when sampling from a normal distribution. Those facts taken together suggest that control limits for medians could be set at process average. There's sigma over root n times 3, but inflated by this kappa value. Process mean minus 3 times sigma over root n for a lower control limit. If one finds any kind of sensible estimates of process mean and standard deviation, those could be plugged into those limits to make retrospective control limits. If one looks at the data on from that dimming drama and says, well, let's operate with standards given. Let's suppose that I know that the mean is 5 and the standard deviation is 1.715. Turns out that kappa for a sample of size 5 is 1.197, and so basically these control limits are a little bit wider than the control limits for X bar, taking account of the fact that medians are more variable than averages, than X bars. If you find the 18 sample medians for the data, there they are, and if you look at already at sample 16, there's the first median that falls outside of those limits, and one would be warned of non-standard process behavior at sample 16. I'd like to close this discussion of control charting for measurements with a couple of reminders. It's worth saying that control limits are not engineering specifications. In Module 25 we said that, and now we say again that the process can be stable without being acceptable, and vice versa. That control limits have to do with process stability. They apply to plotted statistics, and they usually derive from process data. Specifications have to do with product acceptability. Apply not to things like averages, but to individuals. They derive from performance requirements.